and today I will talk about Lie algebras generated by finite sets of derivations. More precisely, I will talk about derivations of a ring of partially Laurent polynomials, but I'll define it later. So the main question that we are interested in during this talk is, when is Lie algebra generated by finitely many derivations finite-dimensional? And to explain the motivation for studying such Lie algebras, I would like to start with some brief historical background. So, a natural source of derivations comes from algebraic group actions on algebraic varieties. Suppose X is a fine variety. G is subgroup of group of automorphisms of this variety, and G is generated by connected algebraic subgroups of group of automorphisms. Each subgroup Gi has a tangent to the algebra, and through the action on X, we can identify these Lie algebras with Lie algebras of polynomial vector fields, or equivalently with derivations on coordinate ring of variety X. So I denote LG as Lie algebra generated by these algebras. And now I think I'm ready to represent a remarkable theorem by Kraft and Seidenberg. It states that, the article was published in 2024. It states that G is algebraic if and only if LG, the algebra, is finite dimensional. And moreover, its tangent Lie algebra equals this.
In the case when it is algebraic.
So in this case, yes.
Yes. So that's why we want to study whether when Lie algebras are finite dimensional, and one of the first general criteria that there is in this field was obtained by one of the university Legenda and Stasiuk in 2021.
Other two people without names, but as a compensation, I'm with two names. But in English, people don't use Vladimir. We just
okay.
In English, this is okay to say only last name.
Okay.
So in Russian, this is when I say Bokovikova, this is something unpolite. But in English, this is no problem.
I'm Bokovikova.
It's a problem because Bokovikova.
Bokovikova. This is really a problem. I agree.
Okay. I get it. So yes. So they studied the vertical locally nilpotent derivations on semi-affine varieties, and I think I should recall what is vertical locally nilpotent derivation means. So we call additive group action vertical if its general orbit is.
It's better to write all this. So,
okay.
Because this is a new concept, it's better to fix it.
Okay. Yeah. So definition. Additive group action is called is vertical.
Maybe you should start with, you have a variety with torus action, yes?
Yes. X is the variety, and in this article that I mentioned, it's semi-affine. GA action is called logical if its general orbit is contained in the orbit in the closure of torus orbit. Yeah, I didn't want to talk about it much. I just wanted to mention that there is criteria for, so there is correspondence between additive actions and opening in derivations, and so we in this article there is a criteria for when the set of finite set of opening potent derivations with a logical is finite generates a finite-dimensional algebra. Yeah.
Maybe let us discuss this a little bit, because if it will be not clear, if somebody don't understand this, then it makes no sense to go further. So first, Olga, let me ask you a control question. And can an orbit of a J action contains not in the closure, but in a T orbit?
No.
No, why? Is it possible that some Ji orbit is contained in some torus orbit?
Think no.
Why? What is the reason? Why closures are indeed necessary? Dear colleagues, please help.
Invertible functions.
Invertible functions. Because when you take a torus orbit, this is as a variety isomorphic to a torus. So algebra of regular functions is generated by invertible elements. So you can restrict this function to this J orbit, and you obtain non-constant J orbits on this. But you cannot have invertible function on J orbit because this is just a fine line. Okay?
I'm sorry, what's written in the definition if it's
General orbit. Orbit.
And I would also prefer plural, not general orbit, but general orbits. Why? Because general orbit, some people like schemes, and this may mean something like a general point in a sense of abstract algebraic geometry. But when you mean general orbit, certainly this is a orbits of general position.
Maybe generic.
Or generic. I don't understand what is better, general or generic. You think generic is better?
So if you use generic, then you can write in singular. Yes.
Okay, and finally, the case of toric variety. Do all people understand that for toric varieties, any J action is vertical? Why?
Because we define toric variety as irreducible that has a toric orbit as open subvariety of subset of the variety. So that's why it is all variety.
So the whole variety is a closure of a torus orbit. So any J orbit is contained in a closure of torus orbit. Okay.
Thank you. Yes, I will not formulate a theorem because it will be, I will need a combinatorial description of T varieties, and I will not mention it later. But also I wanted to mention an article by Matveev. He studied also T varieties and studied the algebras generated by two locally nilpotent derivations. One is vertical and the other is horizontal. And he also obtained a criterion for this case, and he also classified these Lie algebras. He proved that they can be one of three types. One is abelian, the other is filiform, and the third is SL2. I just wanted to mention it. And later, I will work with polynomial rings and, as I said, partial Laurent polynomials, and with graded Z and graded algebras. So, should I recall what homogeneous derivation mean?
Okay, briefly.
So, algebra A is Z and graded if there is decomposition into direct sums of subspaces AU, and we call an element from, we call AU is homogeneous component, an element from homogeneous component is homogeneous, and homogeneous derivations map homogeneous element to a homogeneous element.
Absolutely. U belongs to what is
You consider only grading by lattices, right?
Yes. And by Leibniz rule, there is a well-defined degree for homogeneous derivations. So it means that D be a homogeneous derivation. There is such a vector from Zn that for any element f from AU, the image of f belongs to the component AU first. But how we can write the form of homogeneous derivations for the ring of polynomials? I write it.
No, I'm sorry, Olga, but more systematically. So now you consider A to be the algebra of polynomials. Please write down everything.
Okay.
Then you will find homogeneous derivation of this, and because, okay, so you now give us the form of this derivation.
Yes.
But it's better to write more on the blackboard. So please say that A is the algebra of polynomials. Because you just do some comments and you don't fix it on the blackboard, but it's better to fix it.
Okay. I think now I want to maybe introduce partially Laurent polynomials because I will work with them mostly, and they kind of part of, I think ring of polynomials is part of them. So definition, ASN is this ring. So the first S elements are invertible, other are not, and we call it partially polynomial.
K is a field.
Yes.
And I guess
It's characteristic zero.
yes.
When S equals 0, when we get polynomial ring. So for these types of algebras, we can write a form for homogeneous derivation.
Firstly, you
And
should
what is a grade?
say about grading.
That and grading as well.
What-
That
what-
and grading, where degree of generator equals
belong to this lattice Z. The standard basis vector, right?
Mm-hmm. Now I can. So homogeneous element, homogeneous derivation have the following form. We should be kind of careful with what PI from. PI is from Z
and what is B and P without indices? Beta and
vectors.
P.
Vectors.
Write down. So beta is a vector of beta I. And this noise, this is because of specific pencil.
It's my pencil.
Mm.
It's new, I don't know.
Maybe it's right. Maybe. It's from. Yeah, it's simpler just to write it.
It seems that it's clear.
No, but this is
Not
wrong.
less than 0, yes?
Yes.
No, but this is wrong.
Um,
Take S equals 0. Okay? Write down S equals 0.
mhm. No, yes, it's wrong because when we have a polynomial ring, then if S equals 0, we can have only one PI equals minus 1.
So it also should be said somehow.
And it's not only for polynomial rings, and then we have it also works in this. So
Seems that, yes, maybe no one PI is equal to minus 1.
no.
No. In fact, this is very difficult to express. So in our paper, we decided just to divide homogeneous derivation
yeah.
into types, because otherwise, in one form, it's difficult to express.
Then I just write it here, but I will introduce two types of derivations.
Okay, let us say for the audience, what do we discuss? So write down some derivation when we need this p minus beta equal minus 1.
For example, element is missing. I will write how they take. we need that only one for polynomial ring. This is where we need that only one exponent equals -1, because if we consider other derivation, for example, sum of 2, these things. I'm sorry. And E is not equal to G when we get a derivation that is not homogeneous.
Okay, so let me explain how I understand. Write down just one partial derivative in the polynomial ring. How can you represent it in the form which you wrote above? Then you will need -1. So please write it down as you're supposed to write this exponent -1.
Okay.
This is equal to just write down this formula. Not on continue. Equal to
No.
continue.
The
Equal.
bottom index is not E. It's just a vector, which is
Okay.
E
Okay.
also.
This is something like Bokovikova. This is not E. This is I. Okay. So continue. Equal to in your notation. No, this will be just one semantic.
But it's okay. It's
Uh-huh.
I.
Okay, so it looks like we can allow exponents -1, and then we can write all derivations in this form. But the problem is, as you told above, that if we will do this, we cannot allow sums,
Yes.
because these are precisely homogeneous LNDs, and sum of two homogeneous LNDs is no longer homogeneous LND.
Yes.
So this is a difficulty with this general form, and it's better to distinguish homogeneous LNDs and homogeneous non-LNDs. So it gives you two types.
What is it?
What? This? Or
Yeah. Did you want to make a definition or what?
This is
The
notation.
statement is
Okay, so
definition.
let me explain. Remember, look at this form. Yes, the claim is that any homogeneous LND, any homogeneous derivation of the algebra, say, for example, of polynomials, has this form. Okay. Example: partial derivative. Can it be represented in this form? Yes, it can, but then you should allow a negative indices. Okay, but so let us assume that here you allow -1. But then, if you will allow for polynomial ring -1, then such expression will give you no longer homogeneous derivation, because sum of two partial derivatives is not. Oh, just think a little. No, it's not homogeneous. Right? So there is a difficulty if you want to represent all homogeneous LND in such a uniform
Yes,
expression.
they all have this form, but with some conditions.
With some conditions.
In polynomial ring, you can say that only one exponent can be equal to -1. And it's the whole block.
But then sum should consist of one semantic.
Yes. All bi's equals to 0 except this.
Okay.
So this was a statement. So every homogeneous derivation of this algebra can be written in such a form with some additional conditions.
Or, more precise statement, any homogeneous non-LND has this form, and then for polynomial algebra, this exponent should be non-negative. And homogeneous LNDs have another specific form.
They can discuss one time, so you should proceed.
that. There is a nice phrase, never mind, and continue.
I wrote the general form because I wanted to prove commutator of two homogeneous derivations. So it's, I guess, proposition lemma.
And these triangular brackets, what are they?
It is a standard pairing, I guess. So triangular basis of each and q equals the sum of multiplication of the y. So let's prove it.
Okay, so let us stay a bit on this. Firstly, this type p plus q above shows that this is a gradient.
Yes.
And also such a commutator can be zero, but this is because this lower index can be
Yes.
zero.
Yes.
You would like to prove this, so this is straightforward computation.
Direct computation.
Seems
No
that-
need to prove.
No need
No
it.
need to prove.
Okay.
So let us save time for our discussions with Avdeev. So.
Yeah, it's quite easy to prove. And as it already has been said, there are two types of this derivation can be divided in two types. One is locally nilpotent, the other are derivations that are not locally nilpotent. I write this form. Type 1.
Now we discuss polynomial ring or
Yes.
partial
Yes,
Laurent.
I guess now I will discuss polynomial. And I won't write the second type because it looks exactly like this, but there is no this condition that we discussed.
You can write down above type 2.
Mhm. Type 2, and we denote it as delta.
Seems that type 2 is for non-negative PIs, yes? All PIs are non-negative. This is type 2 for polynomial ring.
Yes. Yes. So, in this article that I mentioned, there is a criteria for when the algebra generated by finite sets of derivations of type 1 is finite-dimensional. It has a combination of ideas from the previous articles, but it formulates for a field of characteristic 0 because before it the field needed to be algebraically closed.
I'm sorry, this is, you discuss Arjantsov, Lie and Stasiuk.
No, I in the article by Arjantsov, Lie and Stasiuk, there is there is a criteria for these derivations, but it's formulated for algebraically closed field.
Okay.
But in this article,
In
in
this-
the article by Arjantsov, Beyfulin, Lopatkin, the criteria assumed that in the criteria it is assumed that the field is algebraically of characteristic 0 but not necessarily algebraically closed. I think I won't formulate this criterion.
Certainly, you should formulate this beautiful theorem.
I see. Oh, no.
No. So
Don't believe in yourself.
do this your way. Maybe.
Yeah, formulate. I think I need because it used graph approach as well. And so basically for the set of derivations, we associate a graph that represents the commutator relations between derivations. So for this type of derivations, graph looks like this. Let D be a set of derivations of first type.
I'm sorry, you started to formulate the criterion, yes?
Yes.
Okay.
Yes. We associate with this set of derivations graph. So of vertices and edges. The vertices are numbers from 1 to n. And there is a condition that an edge, there is an edge between vertices L and J. Definition. If the L coordinate of vector AG greater than 0. That basically means that
Sorry. A of G with E of
I.
I of L.
I of L. Okay. And and A of G.
So the lower and the upper indices depending on G.
Is it a directed graph or not?
Yes, it is a direct graph.
So please give us two concrete derivations and explain that they should be connected by such an edge.
Okay. Let's dr.
Concrete.
d1 and x1 d2.
These are vertices. These are two vertices. And where is the H? H.
Sorry. So we have that vertex comes from.
Let us represent these derivations in this form. Nabla with some indices. The D1 is what is nabla. No.
Concrete values.
Will. Oh, I'm sorry. Yes. Minus E1, I believe. Minus E1 in the
Minus
up.
E1?
Minus E1.
A1.
A1, yes. And A1 in the bottom.
No, I guess if we
Okay.
write,
One. Here is one. And
1 and 0. Because
no.
0. 0 vector. 0
Okay, yes, you're right. 0, 0. now it's good.
So explain, how do you understand that these two vertices should be connected?
So the first coordinate of the upper index of number 2 greater than 0, then from the
Yeah, you're right.
No, I'm not. That's why this direction is correct. Yes. So that means that
The first coordinate of the second vector is non-zero.
yes.
Is greater.
And the second coordinate of the first vector
Vector
is 0
is
because of this, so there is no the opposite.
And
arrow.
I think we don't have loops, right? We never consider L equal to K.
Sometimes you have loops. If you have no, you have
No,
not
no.
loops. Yes.
We
Okay.
don't consider.
Loop is
Because it represents finite derivations, so it's
Okay, so we have a finite graph oriented, or directed, some people say, such that the set of vertices is a finite collection of homogeneous LNPs, and we have edges with respect to defined by this rule. Okay.
And now we can formulate the criterion.
Such a beautiful theorem deserves to be formulated on a new black.
Okay.
So now you consider the case s equal to 0, right?
yes.
Only the polynomial ring.
Yes.
Now Ola observe the previous results, and so they have in the case s equals to 0.
Look, Arjantsev and Gayfulin, these are first letters of the last name, and Lopatkin Victor. This is the first.
We can just remove him.
Don't make such jokes.
So the algebra generated by these sets of simulations, I denote it this way, is finite-dimensional if and only if a graph associated with these sets either there are no arranged cycles
No.
Or all the vertices that are contained in the are contained in the arranged cycle. Correspond to the derivation derivations for which this condition holds.
Why V-oriented cycle?
Is there a unique or
Any oriented set, maybe. For
Why
any oriented.
V-oriented cycle? Is it always unique?
In
No.
Can you
No,
have
no, no.
two cycles
Okay.
of all oriented?
In an array.
Any maybe.
The content again written cycle. This one.
But I don't understand. So this A, they are defined only for first type.
Yes, it's only for that string.
So if we have oriented cycles, then only the derivations of the first time should be included in this cycle, right?
This is criterion for type 1.
Type 1. D is a set of derivations.
Now we consider only derivations of type 1.
Yes, yes.
And what is this clever condition? Sum minus 1 equals 0.
Sum equals 1.
But what does it mean, sum equal 1? Because these are non-negative integers.
Yes, and this means that this is just a partial derivation, yes?
Yes.
No,
No.
because one of these indices A should be 1.
Yes.
So the derivation should be something xj partial derivative I.
Yes.
Now let us write down this is equivalent to
This is
What?
current to x g.
Okay. Yes.
only such derivations can be included in the oriented cycles.
And now I want to talk about the second type of derivations. And we can associate.
Now, maybe we still have time.
Mhm.
Can you give us an example when we have such cycle and what will be the
So that,
final?
in this case, it's no interest.
This is of great interest. So let us give such example. Okay, and something outside of this cycle.
Outside.
No. X1, D1, it's not a local nilpotent derivation.
Oh, I'm sorry.
X1, D2.
Yeah, I'm sorry. Waveform cycle and something that is not in this.
And something which is outside, what will it be?
For example, T1, we considered it in this, so I should write it correctly.
Like this. So 3 vertices, 1 cycle of length 2 and 1 vertex outside.
Yes.
So which algebra will generate these 2 derivations which correspond to this cycle? SL2. And in fact, these cycles, they always correspond to SLN subalgebras.
Yes.
And these points which are outside of cycles, they correspond to nilpotent radical of this finite dimensional algebra. So this graph describes the structure of the corresponding finite dimensional algebra. Let me remind you that there is one more blackboard. Do you resolve this for some other?
I was asked not to go there.
Because of camera,
Yes.
No, you may.
Okay.
there is some person on the control.
Okay. Now I want to talk about the second type. And we can associate a graph with the set of derivations, and I will use annotation, this notation. Now I guess I will talk about partially around the polynomial. So the all indices represent which algebra we are working with, and the upper index represents how many derivations we have. And graph also set of vertices and edges. so it's numbers from 1 to n, and edges. For edges there is a condition. So the pair IG belongs to a set of edges, if and only if that beta I and beta G are not proportional. And this pairing does not equal 0.
I'm sorry. Now you just say something about this article Аннотация Гайфуллин-Лопаткин. Now you move to the case when S is not equal to 0, and you will formulate the general criterion for which for S equals 0 we obtain criterion from this article, and for S not equals to 0 you obtain new result.
Yeah.
Am I right?
Yes, yes.
Okay, and for this case you interested in non-local and important derivations, yes?
Yes.
Am I right? And the condition that derivation is not local and important is that all the pi which is not belongs to, so all pi is non-negative.
Yes,
Yes.
yes.
For non-invertible variables.
For non-invertible variables, pi is non-negative. Yes.
Yes.
Okay.
So let us fix just.
And this graph is not directed.
It's also directed.
This condition is symmetric.
No, it's not symmetric because beta I and pj.
Oh, it's P.
It's p.
Okay.
It's better to distinguish.
Okay, I formulate the criterion. The algebra it's for the polynomial ring is finite-dimensional if and only if the following conditions hold. No, I'm sorry. We can renumber the vertices in the way that the following conditions hold.
Up to renumbering, okay?
The following. The first one is beta I and beta G are proportional. Then beta I and pi minus pj equals 0, and otherwise if g greater than I, and then g equals 0, and there is such a non-negative integer number such that equals 0.
what does the second condition means in sense of graph?
It means that there is no directed cycles in the graph. And I wanted to represent, so it was about polynomial rings. I want to represent. No?
Olga, I understand that this is one of your first talks in your life, but students always think that mathematicians are those people who like to consider some difficult conditions and some long formulas, but this is not true. You should explain somehow the meaning, what happens.
Sorry, this, I don't know, looks kind of unsettling because we have a pairing of objects of like different nature, right? So beta is a tuple of scalars and p is a tuple of integers, right?
It's okay.
And that's
It's okay.
intended, right?
No, but this is clear. Why?
This is because of this formula. Just you can check it.
Oh, it was even earlier.
No, but this is very elementary talk, so I want you to understand all of you. This is why I make such comments. This is clear why we have a mixture of these different objects. Because look at this. Take a derivation in xi. After such derivating, this exponent will go down, right? And this will be multiplied with the corresponding beta. And you obtain products of this pi and beta I. Okay? But what this condition means?
As you said, the necessary condition means that there is no directed cycles. Also, it means that if you have proportional derivations with proportional lower indices, then the commutator should equal 0. And also, this is also a condition on the commutator, but at some point you should get 0. So you commutate I3 times and you get 0.
And can you give us some example, just to see some concrete derivations and illustrate these conditions?
I wanted to introduce an example, but can I talk about the example I wanted to present? I think it would be clear why it has this way. So
Would you like to please? Would you like to discuss type 1 in the case when s is not equal to 0? Let us say a couple of words.
okay.
Just don't write down anything. Just say.
So the first step is locally nilpotent derivations. When we get invertible elements, then partial derivatives of these variables are not locally nilpotent. That's why the set of locally nilpotent derivations gets smaller in some case, and so
all LNDs on partial Laurent polynomial ring, they are LNDs in on polynomial ring, and so new criterion you need not because it's just part of the previous.
Yes. There is no need for new criteria because they have the same form, but it's kind of less. I wanted to formulate the necessary conditions for the algebra to be finite-dimensional, and it applies to the ring of partially Laurent polynomials. It's finite-dimensional. Then graph shaped with this set of polynomials does not contain cycles whose lengths are greater than s plus 1. And for any possible cycle, the sum of exponents of corresponding derivations equal to 0. So
Exponents, this is upper index.
yes, it's up.
This P.
Mhm.
P, I.
Mm.
Okay, okay.
And I would like to show why this bound is precise. So there is a set of s plus 1 derivations. Consider set of s plus 1 derivations. So E less than S.
This is nice that you use this notation, but can you continue and write down what are these derivations?
Okay, yes.
Yeah, but first, okay, don't erase, please. Just, but I believe that minus this sum, yes, because
Minus the sum,
sum
yes.
of exponents should be 0.
Yes, minus. So
Just rewrite this.
it is x I and this is
The XS square, yes? The index is not clear.
Yes, S.
XS. Yes.
and we have these derivations. I want to notice that the pairing that we considered it is equal to 1 if j equals I plus 1, minus 1 if I equals g, and 0 otherwise.
So you can draw the graph. Yes.
Yes.
Please erase
I don't need this calculator.
this is just a cycle,
Yes, just a second.
but with s plus 1 vertices.
Yes, s plus 1 vertices. It's actually the algebra generated by these derivations isomorphic to SLN plus 1.
S plus 1.
S plus 1.
Yes.
I wanted to show it because I think it's quite clear from this condition we get that our derivations, commutator of derivations, equals
Maybe first of all, let us discuss a little bit. This is finitely dimensional algebra, so the conditions are true, yes, because you have not cycles of the length more than s plus 1,
yes.
but you have a cycle of the length s plus 1 and the sum of exponents equals to 0, yes?
Yes.
What you would like to show, yes?
Yes.
And now we show that this algebra is S plus 1.
Yes. So this condition gives us that when we consider a commutator of two derivations, we get either, if we consider neighbors, when we get derivations which lower indices, lower index is equal to lower index of derivation that with bigger index and 0 otherwise. And also we can note that if we consider commutator of all derivations starting from some point, will be a derivation with 0 exponent, and the lower indices will be equal to beta I. So, and actually, all the non-zero commutators correspond to the path in the graph. So I write it this way. Equals to some have derivations of such form. And to construct an isomorphism with S plus 1, I introduce new notations. Why do I need it? Because this way all the exponents will have the same form, and there is condition holds. And maybe I should emphasize that S plus 1 equals S plus 1. And basically, we define a linear map from the algebras.
Maybe vice versa. This P, which is S plus 1, maybe epsilon 1 minus epsilon S plus 1.
Epsilon 1.
Because look at the formula for PI.
Because the
This
sum
is the
should be
next
zero.
one, the next one minus the corresponding index. So the same should be with S plus 1.
Yes. So I've told earlier that if we consider a pattern graph that starts from some point, for example 2, and ends in 1, when we get a derivation with the exponent equals to 0, and then we compute something with a derivation with exponent that is equal to 0, when we get a derivation that is proportional to the derivation that we are computed with. We can notice by this formula, for example, if Q is 0, then we get this derivation. Oh, I'm sorry. And we have as different derivations with zero exponent, and it will, so I denote it as I.
It seems that it's rather complicated. So you just form the basis of this algebra, and you construct a direct
Yes,
isomorphism with S plus 1.
Yes.
Just this should be
Yes.
the basis vector, and so it's just somehow direct computation that this is.
Yes, it is a direct computation. This commutator, it maps to matrix or unit. If E is equal to J, and if and otherwise it maps to, so the whole path maps to matrix of units. That's how we get an S plus 1. So I don't have much time, yes.
Yeah, you have some. And should you say something about S equals to 1? This is just
Okay.
not a criterion. This is
This is a necessary condition.
necessary condition.
And actually, when S equals 1, then we have a very easy structure of the graph. We can have only cycles of length 2. So that's why it was possible to prove the criteria for this case.
Please formulate this
And
criterion.
this is not the criterion because there are no counterexamples, right? It's just difficult to prove.
Yeah, I haven't proved it yet. Should
But
I-
you have not counterexamples, so this is maybe this is criterion, but this is unproved.
Yes.
Okay, and please formulate the criterion in case S equals to 1.
Okay.
Just to, you have two theorems. You have to formulate one.
It's almost exactly like the theorem from the article by Laurent.
It's a pleasure to see this beautiful theorem the second time.
Okay. Finite-dimensional up to the numbering. And these conditions hold. The first one. If same condition that the derivations with proportional low indices should compute. And the second one, so basically means that we have one cycles which lengths equal to, and these cycles correspond to the vertices, derivations, the sum of exponents equals 0.
How to understand about cycles of, how can we construct cycles of length 2?
For example, we can consider derivations with this exponent and this exponent and this exponent.
So this is first case
Yes.
with proportional what? Beta.
Beta.
you write beta and p very similar.
Now
So-
it became even more similar. This is P, right? The second one. Oh, no, this is beta. This is
Sorry, I do not understand. Where here is...
These conditions, they apply to the derivations which sum of exponents doesn't equal 0.
not clear.
So if if we can have two derivations in the set, such as some exponents equal 0, and the algebra will be finite-dimensional.
Sorry. If you have two derivations with the exponentials, summa of exponentials equals to 0, then they belong to the first case or the second?
We don't belong to these cases. The doesn't equal 0, that doesn't equal 0.
Okay. In the second case, you have conditions for these derivations such that sum of pi's is not equals to 0, yes?
Yes, yes.
And
For
for
both.
sum of pi's equals to 0, there is no condition.
There is no condition.
Okay, now it's clear. So you have this example in this case because it corresponds to sum of exponents equals to 0, yes?
Yes.
Okay.
So, wanted to introduce some lemmas.
So what is the aim for the end of this talk? What is your last aim? What are you going to do now?
I wanted to show why graph can't have subcycles, have this graph structure.
The idea of the proof.
Yeah, the idea.
No, it's too much.
Not.
We can stop here. If you can give us maybe one more example, just to see what happens, because this is too formal.
Okay. Maybe.
Say, give us two homogeneous derivations which generate infinite dimensional in the algebra.
So, for example, I will list this case.
And write down what is this
No, I'm sorry.
concretely.
I'm sorry. 1 minute. I guess -1. So this is it's x1 x1 1 plus x2 2.
Mhm.
This is x2 minus 1, x1 1 plus x2 2.
So your conditions show that the algebra generated by these two elements is infinite dimensional.
Yes.
Okay.
And one more example.
Maybe it's interesting to introduce this example in case when s equals to 1, just two than this. The first one, okay. The first one should be what
I write it.
You have not the first,
Yes.
just the second and the third.
Mhm.
X square delta x
No.
or minus.
Mm. One. And
And the second is the power minus 1 d1. And these two generates SL2, yes?
yes.
Nice.
Maybe we should stop here.
Okay, any questions? Comments?
What kind of semi-simple algebras we can obtain by these derivations?
We can obtain this algebra, it is simple, and we can. But the question of classification is the next question that we are interested to research.
So that's the reason we can obtain SLN, but you don't know yet.
Yes.
Of course, you can obtain some copies of the SL, but it seems that you can't obtain something simple algebras of different types. But I'm not sure, but it seems that.
Is there any simple explanation why in Argent's theorem we obtain only SLNs? Why there are no question of
Okay, I'm ready to comment. If no more questions, then I would like to make a short comment concerning all these activities, because in my opinion, I like it very much, and so let us consider polynomial algebra, very basic object, right? So no doubts that we should study this. So just one next step, we consider the Lie algebra of derivations of this algebra. W, this is the Lie algebra of derivations of the polynomial algebra. We know that this is an infinite dimensional simple Lie algebra. It has very explicit form. It consists of all sums of this form. Right? Okay? You can ask, which finite dimensional subalgebra do you have here? You have here no ideals, so you have no factors. But you may have many, many subalgebras. Even the case of one variable is reasonable. So you may consider W1, and this is an infinite dimensional algebra. This is the algebra of the form some polynomial, and we studied some years ago, or we gave a complete classification of finite dimensional subalgebras here. Say you may find here SL2. This is not immediately obvious, but this is the case. Okay. But if you consider the question for arbitrary n, which finite dimensional subalgebra can you have here? The answer is any, if you consider all n. Because here you have as a subalgebra Gn, and it's known that any finite dimensional algebra, this is called Aldous theorem, can be embedded into some GLN for an appropriate number n, right? So you can meet all finite dimensional algebras. But one restriction, this algebra has a very nice gradient. Natural gradient, this algebra has a natural gradient. This is a fine gradient, so all homogeneous components are one-dimensional, natural gradient by multi-degrees. Okay? This gradient induces the gradient on the algebra derivation. So this also will be a sum of such points, and this will be all homogeneous components will be
Not very good. Two indices n.
This is u.
This is u.
N. This is a huge difference between u and n, but maybe I should take another pencil. Okay? And it turns out that all such components are finite dimensional, namely, the dimension of this component is either 0 or 1 or n. Only server n's are possible. We have dimension n if n, this will be eu, and this will be n. So we have dimension n if all this n is this u is some vector. So all if all coordinates of this vector are non-zero. We have 1 if it corresponds to homogeneous LNDs.
Not zero, but positive.
Yes, positive, non-negative. We have 1 if it corresponds to homogeneous LND. So this is the case when exactly one coordinate is -1 and other are non-negative. And we have 0 other ones. Okay? Such a beautiful gradient on this simple infinite dimensional algebra. Okay? So we can ask about homogeneous finite dimensional subalgebra. And I would like to claim that the question is not solved. Oh. But we consider it in two particular cases. So all homogeneous LNDs are divided into two types. All homogeneous derivations are divided into two types, homogeneous LNDs and homogeneous non-LNDs. And we solve this problem when you consider subalgebra generated by homogeneous LNDs, and we solve this problem when we consider subalgebra generated by homogeneous non-LNDs. But mixed case, we are still unable to classify. Okay? And what turns out? It turns out that you can associate some graph with this. And this graph should have the following form: some cycles, maybe 2 cycles, and then some, I don't know, path without cycle. And it reflects the decomposition of a Lie algebra into semi-direct product of semi-simple part and nilpotent part. Okay? Why only SLNs? This is not a proof, but this is somehow theoretical explanation. This is connected with beautiful theorem by de Mazur. If you take a complete toric variety, then you know that de Mazur describes the automorphism group. And that, it follows from him results that this is a linear algebraic group of type A. So the Lie algebra of this group contains semi-simple part, which is only the sum of SLN. So this is exactly the same result. Because you can interpret this as a, we have this gradient, so we consider a fine space as a toric variety with a standard torus action. Mm-hmm. And this is not exactly the same, but this is something close to the Mazur result. Okay?
We should make complete variety, so we should factor.
No, but right. So this is not exactly the same, but this is some analogy, some variant of the Mazur theorem, and the reason is more or less the same as in the de Mazur case. But also, why I like this result very much, because of these conditions. Namely, with these numbers R, I, J. If you study, say, if you take some, I don't know, physicist or mathematicians who study differential equations, if you will ask them about Lie algebra, they will say that all Lie algebras are semi-simple. No answer. Because general audience, they consider, they know only semi-simple Lie algebra. This is well-studied theory with this root systems and so on. But we know that there are other Lie algebras, like nilpotent and so on. And there are mixed Lie algebra, which are semi-direct product. But there is no developed theory of nilpotent Lie algebras, because there are too many of them. We have theorem like in appropriate basis, finite-dimensional nilpotent algebra can be written in triangular form and so on, but can we classify them? Yes, we can. In small dimensions, there are some lists, but say starting from dimension 10, this classification is already not observable. This is huge. But what is very welcome to construct some concrete types, some concrete examples of nilpotent algebra. Do we have such important types? Yes, we do. If you know, there are filiformly algebras. Beautiful, concrete, well-studied class of nilpotent algebra. So my expectation was that having this, we obtain interesting class of nilpotent algebra. They are described by certain matrix consistent of integers of these numbers. So I give you some matrix of integers, and you obtain some very nice finite-dimensional nilpotent algebra, realize it as a Lie algebra of derivations. So if I will have time sometime, I don't know when, I hope to study this class of finite-dimensional nilpotent algebra corresponding to this matrix. Okay? So this was the idea of why we decided to study this. Okay?
Everything here concerns only commutative algebras, right? Because
this algebra is not commutative.
No, A.
Yes, we consider only derivations of commutative
If we
polynomials.
consider, I'll say, Clifford algebras, then I bet we can get like orthogonal Lie algebras, no?
Yes, maybe. So this theorem, which we, from the point of view of semi-simple algebra, is not interesting because we obtain only sums of SLN. But if you want to realize other classical or exceptional simple Lie algebras, then you can look for derivations of some specific algebras. This is known how to realize, say, exceptional Lie algebras as derivations of sums. This is not a task of this project. This project is, firstly, to understand better this infinite-dimensional algebra by listing its finite-dimensional algebra. And also another task is to construct some well-presented and maybe interesting nilpotent algebras. Okay? So this is my comment. Okay, so let us